let's do this again. All right, so I've been asked to do number 14 on the homework. So you're given that you have glass, and I'm going to use this, and glass, we have, it's, move this up a little bit more. Glass, you have the specific heat of glass, so Sg, specific heat of glass, is 0.840. For water, specific heat of water is 4.184 joules per gram degrees C. And then you're told that 1,275 grams. And the initial temperature, this is the mass. The initial temperature is 95. And for the water, you're told that you have the mass of the water. This is the mass of the glass. It is 935 grams. And that the initial temperature is 5 degrees C. And we want to find the TF. All right, I'm going to move this over now. You guys can see all the lovely files I have on my desktop. All right, so to do this problem, we have the Q of the glass plus the Q of the water equals 0, which means I'm going to do it, the mass of the glass, specific heat of the glass, TF minus TI of the glass, plus mass of the water, specific heat of the water, TF minus TI of the water equals 0. So when you have two things in contact, the law of conservation of energy comes into play. The sum of the heat changes is 0. So now I'm going to plug in the numbers. 1,275 grams, 0.8. And if you do, I didn't do this step last time because I was a little short on time. I didn't make the list. And that does help avoid putting the wrong numbers in the wrong place. The TI of the glass is 95. All right. The mass of the water is 935 grams. The specific heat of water is 4.184 joules per gram degrees C. And then TF minus 5 degrees C equals 0. All right, so now I'm going to do some math. I'm turning the light here. All right, so I'm just going to multiply the 12. So if you get to here, you've got the setup. And I'm going to go through the sig figs with this, which will answer that initial question as well. So now I'm going to multiply the 1275 times the 0.840. That's going to have 3 significant figures. Also, grams will cancel. I'm going to keep an extra digit and make a note to myself that the 7 is the last sig fig. This is joules per degree C times TF minus 95. Okay, put that in parentheses as well, just so we can see my sloppy handwriting. Similar to the 935 and the 4.84. Well, also 4.184, excuse me, drop to 3 sig figs. I like to keep an extra one. So 3912, but the 1 is my last significant figure. Again, you can underline it. You can do whatever you want. Joules per degree C times TF minus 5 degrees C equals 0. Now I'm going to multiply the 1071 through the parentheses. So 1071 joules per degree C times TF, and the 7 is my last sig fig. 1071 times 95 is 101745. Oh my goodness, 1017. I'm just going to call it 700. I could call it 745 if I want, but you know, I just don't want to punch all those numbers in, but I have 3 sig figs, and that's going to be joules. Here, 3912 joules per degree C times TF. And then the 3912 times 5, whoops, that's a minus sign because it's a negative. That's going to drop to 2 sig figs. So that's 19600 joules, and that has 2 sig figs equals 0. And the reason I have to keep track is because I'm going to add. So now I'm going to add the 1071 to the 3912, and you see the guess is in the ones place. So 4983, my guess is, I'm sorry, it's in the tens place, my bad. Joules per degree C times TF, that's a parentheses. And then I'm going to take the 1017 and the 19600. So here the guess is in the thousands place, here the guess is in the thousands place. 101700 plus 19600. So my guess is in the thousands place, 121300. Joules, my guess is in the thousands place equals 0. So then moving this over, 4983 joules per degree C times TF equals 121300 joules. The 1 is my guess here, the 8 is my guess there. So I'm going to divide it by 4983. And my final answer is 24.3 degrees C. All right.
For that last step, you did the 121300 divided by the 4983. Is that right?
Absolutely.
Okay.
All right. So that's just like the last one I did. I do apologize for the handwriting, but I'm, that's just how that is. All right. As long as I'm here, I want to pull up one more thing that we're going to need in a little bit before I forget. If I can find where I put it. Where is it?
Would 24.34 be wrong?
Yes, because it has 4 significant figures, and you can't have 4 significant figures.
Okay.
I don't have it. Oh, there it is. Just want to pull that up. There we go. Okay. All right, minimize this. All right, so quick questions about this problem, then I am going to go ahead and go forward with new material.
No, that helped. I must have forgot that equation you used there.
Okay.
Yeah.
And again,
I looked it up.
yeah, I do have office hours tomorrow starting at 8 a.m. Yeah.
Sorry, mid-step through, I was struggling to find the homework to set up the problem, but it's like, so after we multiply 275 grams times the 0.840 or the
Yeah.
the Q or Q of S or J over grams degrees Celsius, do we multiply times temperature final minus 50 C or 5 degrees Celsius, or do we do that at the very end?
So here you can see the cursor, right?
Yeah.
The 3912, or even here, the 1071 times TF, 1071 times 95. That's the 101700. The 3912 times TF, the 3912 times 5 is this number.
Perfect. Thank you.
I see one thing in the chat. Where's the chat? Okay, yeah. Office hours tomorrow. I'll turn on Zoom at 8 a.m. and I'm going to be home, so it'll work better. And then and I'll go. And then during lab, remember, we're not doing anything new. So if you want to even come by my 11 o'clock labs or 11:10 labs for lecture questions, that's fine. Okay, but all right, let me clear this.
One question I had was, how did you get the 4983?
Here, I added the 1071 to 3912.
Oh, okay, thank you.
All right. All right, so what I want to do now, we've gone through elements, we've gone through the types of matter, what matter is, and all that. We spent a lot of time on problem solving. And so what I want to do now is go into the nature of matter. So, in chemistry, we believe that there's a relationship between structure and function. Let's just kind of move this stuff around so I can try to see a few things. All right. Someone asked in the chat when oh, you got it. Okay. And so let me start with some early theory. And that's called Dalton's hypothesis. And like I said, the plan Wednesday is to do an exam review, but if I don't quite finish the lecture material today, we'll wrap it up Wednesday and then we'll spend the rest of the period doing exam review. But this is the last set of material. This is the stuff that's on homework 3. And homework 3, I'll have you just turn in by hand. So there's not a space in Canvas to turn it in. And it'll be due the day of the exam. And I'll post the answer key before it's due. So everyone will get it right. But do not print the answer key and turn it in. I want you to do it by hand. Okay, I mean, if you want to type it, that's fine, but don't print the answer key and do it by hand. Yeah.
Sorry, Professor, real quick. Returning to class or on campus, was that the 22nd or 23rd?
Our class is the 23rd, but classes, depend. You just have to look at your class. Different classes are going back at different times. My Tuesday lab on the 22nd.
But your Monday lecture.
Well, because Monday's a holiday.
Oh, so we won't even resume class until Wednesday.
This class will meet, right, we'll meet face-to-face on Wednesday of next week. We're going to meet Wednesday of this week through Zoom. Next week, we're going to meet face-to-face. You're going to take an exam that day. It'll be all
Gotcha. Okay, thank you.
Dalton's hypothesis is going to look kind of like kinetic theory, just a little bit. All matter is made of, I kind of combine things a little bit from the way they do it in the book, indivisible atoms. All right, so the word indivisible, what does that word mean?
Does that mean you can't break it up?
Right, that's right. And another way of saying this too, this is true, the smallest piece, this isn't really Dalton, but I'm going to, of an element, is an atom. All right, that's kind of a nice, another thing. It's not really Dalton. Dalton didn't actually say this, but they're made of indivisible atoms. So atoms are the smallest, they're the fundamental particles, so to speak. Atoms are the same element. Oh, by the way, don't forget today's Valentine's Day, if that means something to you. Are alike. So that means, let me, where's that periodic table here? Oops. I got to turn on, you can't see the periodic table, can you?
Yes, we can see it.
Oh, you can see it, okay. So if we look at a periodic table here, let me make this a little bit, I'm gonna kind of click between it. Okay, the periodic table, we're gonna start looking at that a little bit today. So what this means though, atoms are the same, element are the same. That means that all aluminum atoms are the same, all iron atoms are the same, all right? Let me just move this over here. Atoms of different elements are different. Kind of sounds silly to say it, but this is in the 1800s. Someone had to say it first. All right, so what that means is if we look at, we don't need this homework here anymore. Let's delete, let's close that. Come on. All right, whoops, too far, damn it. Back up. Okay, what that means is that the difference between, say, lead and gold, one more try. There. If you look at, say, lead right here and gold right here, the difference between lead and gold is actually at the level of the atom. So it's the atoms themselves, all right? that are different. It's not that gold atoms are arranged differently than lead atoms, and the atoms are the same, and they're put together differently. It's the atoms themselves. Someone asked, where can you get the the recorded lectures? They're in that first module. Okay, I'll show you on, let me just show you real quick on Canvas. Is that it? They're right here in the very end, where the first 3 weeks module. All right. Atoms combine in whole number ratios to form compounds. Okay, so what we mean by that, let's kind of make some space over here. If I look at water, okay, water. So we haven't really talked about formulas yet, but in a formula, the subscript goes with the element that immediately precedes it. So this is hydrogen to oxygen in a 2-to-1 ratio. So we don't bother to write the 1, a 1 is understood. Now, mathematically, we could say it's 1 to 1/2, right? For every 1 hydrogen, there's a half of an oxygen. But what this is saying is it can't be that way. It is a 2-to-1, not a 1 to 1/2. Mathematically, that's okay, but chemistry, that's not. Why is that? Why can't we have it? Why can't we write H and then O 1/2?
Because it can't be half an atom.
Exactly. If atoms are indivisible, then there can't be fractional amounts of atoms, right? That's all that means. So it's going to be a 2 to 3, a 5 to 7, something like that. And then the last piece, atoms of the same elements can combine in different ratios to form different compounds. It's like Lego. You take the same stuff and you put it together differently, you get different stuff. All right. So what I mean by that, let's okay, here we have water, and then which is hydrogen and oxygen, a 2-to-1 ratio. And we know a lot about water, right? We need water for our bodies because there's a lot of reasons. Water is a clear, colorless liquid at room temperature. It boils at 100 degrees Celsius. It freezes at 0 degrees Celsius. Just for fun, is water a reactive compound? What do you think?
Yes, water is a reactive compound.
Absolutely. Actually, water is quite reactive. We don't really think of it that way because but one of the reasons our body needs water is a lot of the reactions that we do metabolically actually require water. It requires water to break down protein, for example. All right. Proteins don't dissolve in water, but water is one of the chemicals involved in the reaction when you break down protein. All right. But another compound made from hydrogen and oxygen is hydrogen peroxide. All right. And that's a hydrogen and oxygen in a 2-to-2 ratio. The same elements put together differently, right? Now, hydrogen peroxide is a clear, colorless liquid. But what do you use hydrogen peroxide for? This is the audience participation card.
Green stuff?
Sterilizing.
Yeah, it's a bleach. It'll sterilize things, right? It kills bacteria. Water doesn't kill bacteria. Water won't bleach things out. When you buy hydrogen peroxide, what's the bottle look like?
Brown.
It's dark colored.
It's a brown bottle. Why is it a brown bottle? Because this stuff reacts with sunlight. It breaks down in sunlight. And so it's in a brown bottle to protect it from sunlight. Now, again, I don't care if you know the properties. What I'm pointing out is that the same elements put together in different ratios, very different compounds. Another example you might be even more familiar with, carbon dioxide, right? Every time you exhale, right? and it's a 1:2 carbon to oxygen ratio. Right? Carbon dioxide is not toxic. If you were in a room that was only carbon dioxide, you'd die, but that's not because of the carbon dioxide, it's because you're not getting oxygen. Carbon monoxide, 1:1 ratio, is a deadly poison. People die from carbon monoxide poisoning every year. So again, my point is, same elements put together differently, very different compounds, right? Organic chemistry, just for fun, carbon, everything is carbon, hydrogen, and oxygen in a whole bunch of different ratios. And there's a huge number of different compounds in those ratios. All right, questions about Dalton's hypothesis? I'm going to clear the screen. Now, this was in the 1800s. It turns out Dalton wasn't completely correct. It turns out that there are what are called subatomic particles. So his first thing, atom is indivisible, not completely correct, but that statement, an atom, I'm going to leave this, I'm going to put this back up here. We'll talk about it for a minute. All right. Subatomic particles that we deal with in this class are protons. We'll abbreviate them with a P. And they have a mass of 1. The mass is actually, I don't care if you remember this number, 1.67 times 10 to the minus 28 kilograms. But we're going to call the relative mass. You know, let me rearrange this. Hang on just a second. Make it like this. Particle, make a little table. Mass, relative mass, and charge. Okay. Protons, there we go. They have a mass of 1.67 times 10 to the minus 28 kilograms. But we're just going to call that 1. We're going to use the relative mass, but I like to put this number here for it. You'll see in a few minutes. And the charge is +1. And you can remember P like positive, pro. Neutrons, I'm going to abbreviate them with an N. They have a mass very similar. It's actually the next decimal place. They're a little bit bigger, but we're not going to go there. They have a relative mass of 1, and they have a charge of 0. And remember, neutron like neutral. And then there are electrons. They're abbreviated with an E minus. They are 9.1 times 10 to the minus 31 kilograms. Now, for the relative mass, we're going to call this negligible. I'll explain that in a minute. And the charge is -1. All right. Now, you may have heard of things like neutrinos and quarks and anti-quarks and uncle quarks and leptons and morons and turons and all sorts of things like that. And those other subatomic particles exist, but those are high energy physics. And for the purposes of chemistry, this is what we deal with. So I've never, as a chemist, gone deeper than this. Of course, I was a biochemist, so I'm dealing with molecules anyway. But for the purposes of chemistry, this is as far as we go. Now, before I go on and talk a little bit more about this, if an atom is made of smaller pieces, why this is still true. The smallest piece of an element is an atom. Why can I still say that if, say, electrons are smaller than an atom? And I'm just going to answer it for you. Go ahead. Very good. Someone put in the chat, protons, electrons, and neutrons are all the same. Exactly. All electrons are the same. All neutrons are the same. All protons are the same. So the smallest piece of an element that still has all the properties of that element is an atom. So if I took, let's just use lead and gold again. If I took an electron from lead and I took an electron from gold, right? And I held them in my hand, and shook them up and put them back in, it wouldn't matter which was which. All the electrons are the same. So once I go down to the protons, if I take protons out of chromium, it's not chromium anymore. Or if I take an electron from zinc, it's not zinc anymore. So the smallest piece of an element that is still that element is an atom. And so that's why that statement is still true, right? Now, this word negligible means it's so small it doesn't matter. Electrons do have mass, but when we talk about the mass of an atom, we don't count the electrons. And the reason we don't count the electrons is they're so small, they don't make any difference. If you do the math, this is almost 2,000 times smaller. I think it's like 18 or something like that. So think about this, just an example. If you go to, well, I'll tell you a story. A long time ago, when my kids were little, we were at a big 4th of July picnic, something like that. All right. And there were several families with us, and we had the giant cooler. And as we're getting ready to leave, I go to pick up the cooler, and a young lady in our group walks up and she goes, "Oh, just a minute." I thought, oh, good, she's going to help me. She opened up the cooler, she took out a soda, and she walked away. Now, was the cooler lighter? Was it lighter when she took a soda out?
Yeah, of course.
You think I thanked her?
No.
Probably not. No. So it wasn't enough lighter. In fact, pretty much the opposite. Another example, and you guys have all, I'm sure you've all done this. You go into a place like 7-Eleven and you buy something that costs $19.99. You give them a $20 bill and you don't wait for the penny change, right? I'm sure many of you have done that. Okay, again, you lost money on that transaction. You basically paid an extra penny, but you don't care, right? Because it's so small. So electrons have mass, but we don't count them in the mass of the atom. All right, questions about that? All right, now I'm going to get into a type of notation here. So let me delete this. Now, this is called isotopic notation. We actually use this right in this part of the class, and then you'll never use this notation again until you deal with nuclear chemistry, which is radioactivity and things like that. Very interesting topic, not even that complicated. We don't cover it in Chem 152 because there's just not enough weeks in one semester to cover that. We decided a long time ago when we wrote this course, let's just leave that. You'll deal with that in Chem 201. Isotopic notation, though, in that notation, we'll use the symbol of the element. That'll be the symbol of the element, okay? In the lower left-hand corner, so X is the symbol. In the lower left-hand corner, there's a number called the Z number. Z is the atomic number. The atomic number is the number of protons. All right, so if I go back to the periodic table here, right, on a periodic table, they put these wherever they feel like they should put them. So they don't follow isotopic notation. So on this particular, and by the way, for an exam, I will always give you a periodic table. I have a whole stack of them in my desk drawer in my office, at least I hope so, unless my colleagues stole them. But I will give you, probably won't, it won't be this one, but it'll have all the information. It has the names and all that. So in this case, it's in the upper left-hand corner. Now, I think I mentioned to you the first time I walked into a room that had a periodic table, I thought, well, what a weird way to, and I told you also that periodic table is a map, and we're going to learn over the course of the semester kind of how to read this map by the time we're done with homework 7, all right, just to put it in perspective. Now, when I first saw it, I thought, well, what a weird way to arrange it. Wouldn't you make it a nice rectangle? Why has it got this kind of break in here? And then what are the numbers? The 1, 2, 3, 4, 5. And at my first guess, I was wrong, but I thought, oh, maybe it's sort of they were discovered. But they're put in the order of the atomic number. So hydrogen is atomic number 1, helium is atomic number 2. The atomic number is the number of protons, all right? So if I was to ask you, what element has 6 protons? You would go, oh, it's C, carbon. You just find it on the periodic table. So if I make this just a little bit bigger for you, I don't know, well, that's too much bigger. Oh, that works. If I say, how many protons are in vanadium? How many protons would be in vanadium?
23.
3. Let's see. Yeah, what element has 20 protons?
Calcium.
Calcium.
Okay, now, if you took the element that has 30 protons and you used it in the room in which you cook, what would you call it? What room do you cook in?
The kitchen?
The kitchen.
And it would be the kitchen sink. Get it?
Oh,
Ah, you paid for that. All right. Well, welcome to my class. All right. But you get the idea. If you know what the element is, you know the number of protons, you know the atomic number is the number of protons. All right. So actually, we don't often write the Z number because if you have the symbol, you know what the Z number is. In the upper left-hand corner, there's what's called the A number, and the Z comes from it comes from a German word. I don't speak German. I don't remember what the word is. A is the mass number. It's related to the atomic mass, but it's not the atomic mass. We'll talk about that before we finish this lecture. Now, if you go back to, well, I erased it. But if I was talking about something, the mass of an element, what subatomic particles would I be talking about? I know I erased it. Protons have a mass of 1. Let me just put this up.
neutrons, electrons, right?
The mass of an element.
I only wrote down 1. I have protons at 1.67 to the 10th or times 10 raised to negative 28 kg.
Yeah, and you, by the way, don't memorize that number. Just remember this here. I was putting that up there for reference. All right, but if I was talking about the mass of an atom, what subatomic particles would I be referring to? What would I need to know?
Protons and neutrons.
Protons and neutrons, right? If I was talking about the charge, I would need to know about
Protons and electrons.
protons and electrons. So the mass number is the protons plus the neutrons. It's the number of protons plus the number of neutrons. All right. The charge up here, that's if any. CH is the charge if there is any. Whoops. So if it's uncharged, there won't be anything there. And I'm trying to explain this in a way that you can just, if you just remember, like protons have a mass of 1 and a charge. If you remember this, you can kind of figure out the rest. And it's really important in the sciences to try to memorize. You have to memorize some things. If you're learning a language, you have to memorize some words, right? But what you really want to get is memorize just the things you have to memorize and then the principles, and then you can figure things out from there. The charge, if any. And if you can kind of figure it out, or you can say, well, it's going to be the number of protons minus the number of electrons. Put that in a circle so you don't confuse it with a negative sign. All right, now, one other thing. An atom has no net charge. Has no net charge. All right, so what can you tell me in an atom about some of the subatomic particles? It's made from charged particles, right? It's made from electrons and protons and neutrons. But if the atom has no net charge, what can you say?
The protons and electrons are equal.
Very good. In an atom, the number of protons will be equal to the number of electrons. Let's make that. Now, a charged particle is called an ion. All right. Now, if the particle is positively charged, it's called a cation, like kitty kitty. It's not pronounced cation, it's cation. And in this case, the number of electrons will be less than the number of protons. And I always want to relate it to the protons because the number of protons is identifying. All right. If something is negatively charged, it's called an anion, like anti. It's not pronounced anion, it's anion. And in this case, the number of electrons will be greater than the number of protons. Just remember, electrons are negatively charged. All right, I want to show you something kind of cool. Let me find this. This is actually on the slides. I told you these slides are optional. All right. But I have a link that I wanted to show you. This is really cool. If I take potassium metal, see if I can, oh, I have to do it this way. Hang on a minute. Slideshow. Can you see the PowerPoint?
Yeah.
I think there's even a note. Again, you guys never have to look at these slides, but I have them handy. If we look at this video, give this thing a second. Give it a second to come up. You guys are going to do this in one of the experiments, I think, unless we cut it out. Give it a minute here. All right, can you see it in the video? Yes?
Yes.
It's only a 15-second video. It takes longer to up. Oh man. Oh, I'm gonna skip the ad. Here we go. Okay, fine. I don't want the ad. HTML block. Oh, it's still loading. Here we go.
Are you sharing your sound too? Because may not be able to hear it.
I don't know. Come on. There we go. Let's go back. Damn it. Where's the potassium in water? That's magnesium, sodium in water. Here it is. Do that one. There we go.
So I've got my essay written, and I've been working on it for about a week. So now I'm going to show you how I use Grammarly to edit.
Okay, let's try it again. There we go.
Oh my God.
There we go.
Oh, that's a good one.
There we go. All right. So you can see potassium in water. It catches fire. All right. Now I want to go back to, let me go back a slide from here. This is what potassium metal looks like, right? See, it literally looks like a piece of metal. This is potassium ion, right? Look at that. It looks very, very different. See that? Okay. So, and also the physical and chemical properties are very different. If I take, you saw potassium metal in water catches fire. Potassium ion in water, if you put it in water, it just dissolves. So I just wanted to point that out to you, and we're going to, and then we'll actually go back to here in a second. All right. So let me go back. I'll go back to that in a minute. Let me go back to, where's my whiteboard? So what's this? This is really a pain in the ass to manage this. There we go. All right. So let's go through some examples of just how many protons, neutrons, and electrons are in something. All right. So remember, just, I guess I erased that, but if we say how many protons, neutrons, and electrons are in various things. All right. So let's go with, how about magnesium 24. All right. So it's really handy if you guys have a periodic table. If you don't have one handy, from now on in class, well, we'll be back in a room, but there'll be one up on the wall. So magnesium has 12 protons. See that? Okay. That means how many neutrons does this have?
12?
12, very good. So there's 24 protons and neutrons. 12 of them are protons. So this, I'll just write this here in case you didn't quite catch that. All right, kind of like, remember when you were in second grade and you learned how to subtract and they gave you problems like, Johnny has 15 apples and oranges. If 6 of them are apples, how many are oranges? Remember that stuff? And you'd say 9, right? Well, magnesium has 24 protons and neutrons. If 12 of them are protons, the other 12 must be neutrons. This has 12 electrons because it does, all right? Because it's no net charge. Let's do another one. Let's go, how about, I don't know, how about zinc? 65. Okay, how many protons in zinc? We did that before. Where'd that periodic table go? Zinc's right here. How many protons in zinc?
30.
30, very good. All right, how many neutrons would zinc have? Right, in the chat, 35, very good. How many electrons would this have?
30.
30, very good. All right, let's do this one. Let's do Fe 56, 3 positive charges. All right, so this is iron. Iron is right here. How many protons does iron have?
26.
26. How many neutrons would this have? 30, very good. All right, this is 56 minus 26 is 30. That's a 0. Right. All right, and how many electrons would this have?
29.
29. Okay, I got one person that says 29 and what?
26.
26
23.
23.
I don't know how much I'll have.
it has 23 electrons. Now, how do we know? You can do it intuitively. You can say it's got 3 more positives than negatives. So it's got 26 positives, there must be 23 negatives. If you like little equations, and I know there's some people just give me an equation and I'm good, all right? Charge is the protons minus the electrons. So if we said in this case, +3 is 26 minus the number of electrons. So -23 would be negative the number of electrons, so the electrons would be 23. So if you like little equations, you can do it that way, or you can do it intuitively. All right. How about, let's go, oh, I don't know. How about, pick something, Rob, it doesn't matter. How about BR 80 with a -1 charge? I circle my charges. You don't have to circle your charges, but I always put a circle around my charges because otherwise I get them mixed up with other things. So there's no rule that says you have to put circles around your charges. It's just a thing I do. All right, so bromine is right here. How many protons does bromine have?
35.
35. Very good. There's 35 protons. How many neutrons does bromine have?
45.
45. And again, 80 minus 35 is 45. Always, always, always do the protons first. Because that way, because if I made it 34, right, that wouldn't be bromine, it would be selenium. Okay, so bromine, 35. And how many electrons does this have?
36.
36.
Very good. And again, you could do it this way, or you can just go, there's one more negative. But you could go -1 is protons minus the electrons. And so -1 is 35 minus the electrons. So -36 would be negative the number of electrons, right? So,
Professor, I'm sorry, I'm a little confused. I was fixing my notes because I was jumping around where we were at. The +3 and then the -1 in bromine.
Yeah.
Does that affects like what we know? So like to get to the number of protons, it's protons plus neutrons, so we get 56. And then to get electrons, yeah, you just minus that out or the remaining number. Like whatever is left, you get 23. Where does that +3 come in? Or what is that +3 plus?
At this point in time, I would give you that. So I'm going to say iron with a +3 charge. How many protons, neutrons, and electrons does it have? How do we know it's a +3 charge? If you're asking me that, that's something we'll come up with later on. So how do I know bromine forms a -1? We'll deal with that later. Right now, I'm giving it to you.
Okay.
Does that answer your question? Is that what you were asking?
I'm just like, I'm confused. Like, does the minus have to do with anything like in this equation? Can't we just
The minus on the bromine? That tells me that I have one more electron than protons. And the +3, and by the way, if you write it +3 instead of 3+, that's okay too. But if you write the 3+, that means there's three fewer negatives than positives, meaning there's 3 fewer electrons than there are protons in here.
Oh, I see. I got you. Okay, cool. Thank you.
Okay, let me just, let's do, there was something that was on that slide. And again, you guys never, for this class, you never have to look at those slides if you don't want to, but they are there for reference. And there's even me doing voiceovers on them, you know, because I did teach this class asynchronously. All right, so just to do this, K39, K plus, this is what I demonstrated to you, 39, P 30, and P 32. All right, let's do that. Whoops, what did I just do? Ding, ding, ding. All right, so again, potassium. Oh, come on. Potassium, don't mix these up either. K is potassium, P is phosphorus. All right. And I think I told you, you don't need to memorize the symbols. You're kind of going to be expected to maybe know the first 20 when you get into general chemistry. But I think, you know, looking things up and writing them down over the course of a semester, you'll probably have a bunch of them memorized just on your own. I will say, you know, times have changed. Memorization is a skill. And because of all the technology we have, we aren't, as little kids, we're not taught to memorize as much as, say, my generation was. And it's not a good thing or a bad thing. It's just different. But when I was a little kid, we weren't allowed to go outside until we knew our address, our parents' names, you know, not just mom and dad, our phone number. So if we got lost, but now you got a phone. So what that means is that, you know, it's a little bit more challenging to memorize things, I think, nowadays, just because you're not taught it as a little kid. That being said, you can always look things up. All right. So there's a giant periodic table in the wall of the lab. And I think I told you, if I was you, I'd print one and stick it on the wall wherever you do your homework. So it's right handy. I mean, there's one in your textbook as well. Anyway, so let's just do the protons here. Potassium has 19 protons. And phosphorus is 15. Okay. All right, and then this is going to have 20 neutrons and 19 electrons. This is going to have 20 neutrons. This has 18 electrons. And then we'll just fill this out, and I'm going to talk about this. 15, 15, 15, 17, and 15. All right, I'm going to finish this stuff in plenty of time today. All right, now I just showed you on those slides. Let me just back it up here. Here's potassium and these two, potassium and potassium ion. All right, so potassium metal, it looks like a metal. Metals are shiny. It's not the best picture in the world, but metals are shiny, and you know, it looks like a metal. Now, a lot of metals, if you look at it, it might not look shiny, but that's because of not all, but a lot of metals react with oxygen in the air, and they form what's called a metal oxide. Metal, like rust, is a metal oxide. Metal oxides typically are black, white, or gray. The one from iron is that kind of orangish color. And a lot of metals will form the oxide right on the surface. But if you take a piece of sandpaper and you scrape it off, you'll see the shiny metal underneath. Some of the metals are so reactive that as fast as you wipe it off. As fast as you scrape it off, it'll reappear. The ion, though, look at this. Potassium ion is a powder, a white powder. So do you agree the element and the ion, that it's the element and an ion from the element, very, very different physical properties. Do you agree?
Yes.
They look very different, right? And I showed you the chemical properties. So this is an atom, ion from that atom. So atom versus ion, very different. We saw chemical, physical properties and chemical properties. Hang on just a second. I don't know who that is, so we're just gonna have to turn it off. Very different properties, physical and chemical properties. We'll just say very different properties. And now structurally, we'll do these ones in a second. Structurally, what's different between an atom and an ion? Structurally, what do they differ in?
Different amount of electrons.
Very good, right? They only differ in the number of electrons. Different number of electrons. That's the only, in this case, it's only one electron difference. You change one electron and you completely change the properties. So an element and an ion from that element are going to differ in the electrons, and they're going to have very, very different properties. Okay. Now, and so that's interesting when people talk about stuff in their diet. You know, my brother got really into, he decided, my brother is an artist and he's an extremely talented artist. He's not a good scientist. So, and he's also not someone who likes being corrected. So I just kind of let him go. But he, decided on himself. He went to the doctor of internet and decided that he needed more magnesium in his diet. And then I was explaining to him, I go, well, magnesium is actually a metal. It's actually magnesium ion. So again, when you say calcium in your diet, right? Calcium is a metal. It's not calcium metal that's in your diet. It's an ion, calcium ion in your diet. You need potassium in your diet, right? Potassium, you get a lot of potassium in bananas. Potassium and sodium are very important for neurotransmission. So for nerve signals to propagate, sodium and potassium have to be balanced appropriately, and those are ions. They're not the element. Sodium is a metal. So again, elements and ions very, very different. They're called the same thing though, right? Now these two are what are called isotopes. Right? Isotopes are atoms of the same element. With different masses. All right, let me erase, well, I'll just do this here. So these are isotopes. P30 and P32 are isotopes. Atoms of the same element with different masses. Now, structurally, isotopes, I'll write it over here. Structurally, what's different about these?
Different neutrons, number of neutrons.
Good. So they have different number of neutrons. I'll just write N for neutrons, all right? So interestingly, if you change the number of electrons, you change the properties. Now, isotopes have nearly identical properties. All right, nearly identical. They differ only in, of course, mass, and therefore density, right? Because the volume, or because the mass changes, therefore the density changes. And then I'm going to write sometimes radioactivity. The reason I'm going to say sometimes is there could be 2 or 3 isotopes and none of them are radioactive, so they would not differ. And again, this class, we don't deal with radioactivity, but I'm going to spend just a couple minutes on it. All right. Radioactivity, and this isn't something I would test you on. Radioactivity is when an atom falls apart. And it's literally when we haven't talked about where these things are yet, but it's when the nucleus of an atom falls apart. And when it does, it gives off a huge amount of energy. Radioactivity can be used for any number of things, of course, weaponry, it's a source of energy. Radioactivity, actually, nuclear energy as an energy source does have some advantages over, say, fossil fuels. It doesn't produce greenhouse gas at all. It doesn't produce carbon dioxide. It doesn't use, there's no methane. You're not burning something. The nuclear power plants as radioactivity as an energy source has some issues. Obviously, if you have if a traditional power plant blows up, it'll take out a city block and there'll be a lot of smoke in the air, right? If a nuclear power plant blows up, it'll take out a region, a much, much larger space, and it'll be uninhabitable for a very long time, like Chernobyl area, in Siberia, that kind of thing. Their safety record is actually quite good. And nowadays, right, most of them were built in the 50s and 60s. If we were building one now, I'm sure our engineering is much, much better. That being said, also the waste disposal issue is a big issue with radioactivity as an energy source, and that hasn't, to my knowledge, really been well addressed. But I don't want to. That's a very interesting discussion, and it's not really a discussion for this class right now. But just pointing things out, because the elements do the same chemical reactions, radioactivity can be used like a tracer. So for some of you may have had a diagnostic test with a doctor where they gave you a radioactive isotope so they could find something. So they might give you like radioactive iodine would go to your thyroid, and then they could get an image of the thyroid much better because it gives off energy. So they can use it for that, just to follow a process, any number of things, because you can detect the energy. Radioactivity exposes film. It also can be used as a means to, it's ionizing, meaning it can destroy tissue. And so, they use radiation to take out cancers sometimes. So those types of things. Actually, a barium swallow they're not using radioactivity. They're just using the fact that barium is very dense. And so you can't, X-rays won't go through it, but it's the same type of thing. All right. So make sure you know the difference between a neutral atom, an ion, and isotopes. So isotopes, you change the number of neutrons. The properties are nearly identical. Ions, it's a different number of electrons. The properties differ significantly. And that also leads us into the idea of, look, interesting, if you change even one electron, the properties are extremely different. But if you change the neutrons, it doesn't do a thing. When we talk about structure, we'll come back to that. Also, if you think about Dalton's hypothesis, if you remember Dalton's hypothesis a while ago, Dalton's hypothesis, remember the elements of the same atom are the same? He didn't know about isotopes. Okay. He also didn't know that there were subatomic particles. All right, questions about this material right now?
Yeah, so we're supposed to know the ion and isotope.
You should know what ions are, what isotopes are. I can pretty much guarantee you on your first exam, you're going to get a problem like this. It says, it might be like, here's something, how many protons, neutrons, and electrons are in there, right?
Okay.
All right, I'm going to turn off the screen share for just a minute, just to talk. I want to pull up another thing.
Professor.
Whoops. Go ahead.
It's fine. I have all that written down. I'm just making sure. So an ion, and what makes it an ion, different number of electrons. What makes it an isotope is basically different number of neutrons. And what makes it an atom is it's neutral across the board.
Right.
Like it
all. Isotopes are a type of atom.
Okay. And then, but an atom in general, like everything's the same. Protons, neutrons, and electrons. Everything's like 15, 15, 15, and we're good, right?
Right.
Okay. I just want to make sure for my notes.
The same. You don't have to have the same number of protons and neutrons in an atom. Remember when we did the zinc? 30 and 30 and 35, remember? They don't have to have the same.
So how would I differentiate an atom then? How would I write that?
Well, an atom has no net charge. Just remember, an atom has no net charge.
Atoms have no net charge. Thanks.
And isotopes they're like different flavors of an atom. Think of them like being different flavors. Okay, they're the same thing, but they have different masses. So a phosphorus 32 and a phosphorus 30 are both atoms. Does that make sense?
No net charge is what I'm.
Right. Yeah, and P30 and P32 both have no net charge. All right, I want to go back to, where's my Zoom? All right, now I want to talk a little bit, like I said, we might finish this right at the end of class. If, like I said, if we spill into the Wednesday lecture, it won't be much. It won't be much of a spill. Let me do a screen share here. Let's go back to this. All right. Now, if protons have a mass of 1 and neutrons have a mass of 1, how come atomic masses, and again, if you look at this, if you look at the periodic table here, atomic masses, right, they're not whole numbers. Like, look at, some of them are close, like hydrogen 1.008, oxygen 15.999, nitrogen 14.007. Right, so you can explain that away because neutrons are a little bit heavier and and that kind of thing. But then you look at something like iron, 55.85, or chlorine, 35.45. So the question is, why are atomic masses not whole numbers? Because if they're made from from things that have whole number masses, they should be whole numbers. And I kind of alluded to it. I'm just going to tell you. And the answer is because they are an average of the masses of the isotopes. So some elements only have one isotope, but some elements have multiple isotopes. And it just depends, right, on the element. And you could look it up. You could look up it. Interestingly, just if you're bored and you want to really nerd out, there's a website called webelements.com. I might have mentioned this. And it has an active periodic table. If you click on an element, it'll give you all sorts of ridiculous information, including how many isotopes it has. It's just kind of to nerd out. All right. Now, the average of the masses of the isotopes, but the isotopes don't have equal occurrences. So there is the average is really what's called a weighted average. So the average is the percent of A times A plus the percent of B times B plus the percent of C times C, and so on. So I'm going to demonstrate something to you, all right? I have here, just how to calculate there. I have here, I think you guys can see these, 2 isotopes of the element paperclipium. So I have 2 paper clips. See that? Okay. Do you agree that these are analogous to isotopes, meaning they're the same thing but different size? That makes sense? Yeah. Okay. So I have, what the hell is that on? Okay. So I'm going to say the element paperclipium. I just made it up. So if you look for it on the periodic table, we're going to use the symbol PC. And there's 2 flavors. There's large, right? This here. And there's small. Now, I've done extensive studies on paperclipium, and I've determined that the large paperclipium L for large, is 35.3% of all the paperclipium. And the small paper, I've never done this demo on Zoom. The small paperclipium is 64.7%. Right? Now, if I put these on a balance, I have a balance over here that you guys can't see. All right. Turns out the small paperclipium has a mass of 0.7054 grams. And the large paperclipium has a mass of 1.2134 grams. So I could use that to calculate the mass of an average paperclip. So the average paperclip is going to be using this formula here, right? It's going to be the percent. It doesn't really, it's additive, so it doesn't matter which one you say first. The percent of the large times the mass of the large plus the percent, in this case, there's only 2, of the small time, like, let's get rid of that stray mark here too. Times the mass of the small, all right? So if I plug in the numbers, and remember we'll express the percentage as a decimal, 0.353 times 1.2134 grams plus 0.647 times 0.7054. And that comes out to be 0.885 grams. Would be the average paperclip. All right. See how to calculate that? Now on, and I'm going to move this for you guys, but on your Canvas site, there is this handout. Where it is, it's under, it's kind of in the module that has this lecture. I'm going to move this handout up into another place. I'm going to, but this handout, it basically, right, if I say sulfur has 2 isotopes like this, right, this is calculating that average. So the mass of sulfur, this is a handout that's on the way. I'm going to move the handout. I'll move it up where I put the recordings. Okay. But if I say sulfur has 2 isotopes, you can assume that the mass of an isotope is basically a whole number. So sulfur 32 would be a mass of 32. Sulfur 35 would be a mass of 35. And so I could calculate the weight of the average sulfur atom if I knew the percentages. Just plugging it in. It's the same equation as I did for the paper clips. All right. Now, what's really interesting about this, let me ask you a question. Okay, I have here in my hand a pile of paper clips, large and small. All right, I don't think you can really see that very well. If I reached into this pile of paper clips and I randomly grabbed a paper clip, and even if I did that 5 or 6 times, would I ever pull out a paper clip with a mass of 0.885 grams? Ever. This is what's in there. There's the large and the small only. The chat, let me open the chat back up. No, that's right. No, I would never pull up a paper clip with that mass. So my question to you, and this kind of is going to lead to somewhere we're going to go on the next lecture, which is going to be after the first exam, right? If the average paperclip doesn't exist, then what good is that average? And the answer is, all right, in chemistry, we have a really interesting problem. And that problem is that we want to be quantitative. That means I want to know how many atoms I have in a sample. But there's no way to do that experimentally. I cannot count atoms for two reasons. One, they're too small to see. An atom's diameter is like 10 to the minus 10th meters. The human eye is good to about maybe 10 to the minus 4th meters. So they're a million times smaller than what you can see. Because you can see like things that are maybe about 1/10 of a millimeter. All right, but not so. And even in a small sample, they're too numerous to count. I mean, you know, all of you know how to count to 10,000, but would you really want to count out 10,000 of anything? No, right? You can't do it. It's me. So how do we do it? Well, remember back, actually, you guys are probably too young for this now, but when you went to the world's most annoying restaurant, Chuck E. Cheese, when you were a little kid, and you got all those tickets for playing whack-a-mole and skee-ball and all those other games, how did they count the tickets? Now they have barcodes on them, but does anyone remember before they had barcodes? Anyone remember?
They weighed them.
They weighed them. They would count by weighing. So we actually count by weighing in chemistry. So just to show you. Now I have a small sample of paper clips here, and the average is much more meaningful the bigger the sample. But if I put all of these on my balance, let me put them on the balance. Okay, my balance says 15.0403 grams, okay? So I have 15.0403 grams of paper clips. And I know from what I just did that one paper clip, the average paper clip has a mass of 0.885 grams. See, we're using dimensional analysis. And so when you do the math for that, 15.0403 divided by 0.885, it comes out to be like 17 paper clips, 16.99. All right, so let's count. Let's see how good I did. I borrowed a balance from work. All right, they won't even know. No one's in the lab. All right, so let's count. 1, remember the count on Sesame Street? 2, 3, 4. This is 2 of them stuck together. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 wonderful paper clips. All right. So I just showed you that you can actually count by weighing even with something like this. And so that's what we do in chemistry. And that's actually stuff that we're going to do a lecture on that after the exam, which will be on the 23rd, the exam. Okay, so the next lecture after that. Now, so that's why we use that average. So let me, now, I want to go through one other problem type just to show you how to do this. And there's something like this on homework 3. Where did I put that thing? So here, here. All right, this is the, like I said, I'm going to move this handout in Canvas up like where I put the lecture. I'll indent it from the recording of this lecture. It is on the Canvas site. I'll show you where it is. But the second problem is just doing it backwards. I'm going to walk through this. We have 5 minutes. I'm going to walk through this problem. All right. So this problem says phosphorus has 2 isotopes, P32 and P30. The experimentally determined mass is, don't worry about the unit right now, 30.97. What are the percentages of the isotopes? And remember that the sum of the percentages has to add up to 100% or 1 if you're going to put them in fractions. So this is that same equation. The mass is the percent of the first times the mass, the average mass, percent of the first times the mass of the first, percent of the second times the mass of the second, since there's only 2, right? And again, don't worry about these units. This is an old handout. I've been saying for 20 years, I'm going to get the units off of here, and then I go back to my office and I forget. The mass of phosphorus 32 would be 32. The mass of phosphorus 30 would be 30. The sum of the percentages is equal to 1. So arbitrarily, let's call X the P32. If they add up to 1, then the other one has to be 1 minus X, because if X is sum of it, if all of it is 1, X is some of it. 1 minus X is the rest of it. So again, don't memorize this. Just think about it. Like getting back to the Johnny has 15 apples and oranges, right? If Johnny has 15 apples and oranges, then 6 of them are apples, 9 are oranges. If he had 15 apples and oranges and X of them were apples, then 15 minus X would be the oranges. It's the same idea. So if all of it is 1, right, then X is some of it, the rest, and that's the rest of it. Then if we plug these into this equation up here, 30.97 was the average. Percent of the 32 we called X. Doesn't matter which one you call X, and the mass was 32. The percent of the 30 here was 1 minus X, and then the mass of the 30 was 30. And then this is the algebra. Okay, doing the math. Okay. There. And so X would be 40.49. X was the P32. And then 1 minus X is 51. All right. And that's one of the handouts. And actually, we got through all the material. So this is all of the material. Let me get out of here. Let me go back to modules. All right, that where just to show you where that was. It was way down here. Where's the isotope problems handout? See that? I'm going to move this up right now. I'll move it up to here. Put it right there. Okay, so now I'm going to indent it. There. The handout I just did is right here. I'm going to indent it too. And I'm going to put the recorded lecture right above this. But you can look at that handout because there's problems just like that on the homework. Now, on Wednesday, so you now should be able to do homework 3. And homework 3, I didn't post here. Homework 3 is way out because all your homeworks from now on are going to be way down here where it says homework assignments, and it is here. All right, it's downward in the module that says homework assignments. That's where that is. On Wednesday, we're going to do this review for the exam. I made the key for the review visible, but I was going to let you guys work on this in class. So don't click on, don't here. Tell you what I'm going to do. I'm going to unpublish that for a minute. There. I don't know if you've looked at it already and you printed it, great. But if you haven't, this is something we'll just kind of let you guys work on this in class a little bit. So on Wednesday, what I'm going to do is I'll open up a Zoom session. I'll answer some questions. Maybe I'll put you guys into breakout rooms and you can work on this a little bit. And then I'll just kind of work through and help you with them if you want me to. All right. And we'll do it that way. And then Monday is a holiday. And with the following Wednesday will be actually in class. Yes, sir. And that's not to be turned in. The review is not to be turned in. Go ahead.
I'm sorry, Professor. Can you go back to where you where the handout was? I can't find it. We missed it. I'm sorry.
It's on the first. It's under the first 3 weeks module. I moved it up.
All right. Awesome. Thank you.
All right. Yeah, I just moved it up to there. All right. So I'm done for now. So, and I don't have an office hour on Mondays, do I? No, I do not. So I'm going to close the Zoom session. I have office hours tomorrow morning. And yeah, go ahead. So those of you who are leaving, have a good day. I can leave it open for a few minutes, answer a few questions. Let me turn off the screen share. I don't have office hours on Mondays. No, I do not. Let's just look at this real quick.
Thank you so much, Professor. Have a great day.
Yeah, I don't have an office hour. Okay. But I'll hang around and answer a couple of questions if anyone has any.
I have a question.
Yeah.
So when you're doing scientific notation, I'm kind of confused.
Hang on 1 second. I'm going to turn off the recording.
Okay.